In this video, I'm going to show you how to graph logarithmic functions by transformations or simply by using a table of values. So you can graph a logarithmic function using transformations by comparing the logarithmic function that we already know, which is y equals log x, to this function here, which I've added a, b, h, and k. So just as a reminder, the a value creates a vertical stretch by a factor of a. And I'm going to write the absolute value of a, and then write it separately that if a is negative, we also reflect in the x-axis. Now the other value that affects our vertical direction is our k. So the k creates a vertical translation by a factor of k. All right, and then we have our b, and this creates a horizontal stretch by a factor of 1 over b. And again, I'm going to write the b in absolute values and then say that it reflects in the y-axis if b is less than 0. And then the other value that affects our horizontal direction is the h. And the h gives us a horizontal translation, and this will be of h. So notice that again it is minus, just like all the other functions that we've looked at before. Now one other thing to point out is notice that there's a c here, and c here is the base of this log. So it doesn't really come into play, and I'll show you how we use it in terms of transformations. So transforming all of this into our mapping notation, we have xy, the a will give us x bracket a times y. The b will be x divided by b divided by y. Oh, sorry, not divided by y, and comma y. And then the h will be x plus h, even though it's minus, and then y value. And then the k will affect our x, so this will be x, and then y plus k. Now we've looked at graphing a logarithmic function before, where it was a basic one. So now we're going to take a look at graphing the logarithmic function with the transformations. So I have all the a, b, h, and k written down generally. So the first thing that you want to graph is this part here where it says x minus h. So we know that this value that we log has to be greater than 0, and that x cannot equal h. So we're going to first draw in our asymptote. And the asymptote here is x equals h. And I'll write this down here. And even if it was the other graph, so where this is c is greater than 1, here c is between 0 and 1, we still will get a vertical asymptote. So this is still x equals h. Now, when c is greater than 1, if you recall, we get a graph that curves up to the right. And when c is between 0 and 1, we get a curve that comes down, curving to the right. All right. Now, the domain, in both cases, x is greater than h. However, actually, let's write this down. So y equals log x minus h. Now, the graph can actually flip to the left side of the asymptote. So I'm going to rewrite this down as well. So x will be less than h if y is equal to log bracket negative bracket x minus h, and then 2 close brackets. So what's happened is that our graph has reflected kind of over our y-axis, and in this case it's also over our asymptote. And then finally, for both graphs, the range is y is all real numbers. So let's take a look at an example. So here we have a function where I want you to transform to sketch the new graph and identify the specific characteristics that I've listed down here. So we're going to start with our basic graph, and our basic graph means that we don't have any h's and k's or a's and b's. So I'm going to rewrite this as y equals log x. So the base here is 10 since it's not written down, so I'm still going to use a base of 10. And let's actually write that down because that's very important. So therefore, what I'm going to do is I'm going to choose values that also have a base of 10. So that means that I could choose an x value of, let's say, 1/10, which is 10 to the negative 1. So that means that my exponent is negative 1. If I choose an x value of 1, the only exponent that would give me this value of 1 would be 0. If x were 10, remember this is a base of 10, okay? So remember that 10 to what power will give me an x value of 10, and that will be 1. And then finally we have 100. So 10 to the power of 2 will give me 100. So therefore my y value is 2. All right. So then to write the transformed function, I can see that I have a -10 and a -1. So originally, if these are the original points here on the left side, the mapping notation would state that I need to add 10 to all my x values and then subtract 1 to all my y values. So my new table will be 10 plus 1/10, and then 10 plus 1, and so on. My y values will be -1 minus 1, 0 minus 1, and so on. Okay. So when I graph this, I'm going to first draw my asymptote, and you can see that that's 10. Actually, what's nice, what I like to write down is that my asymptote is 10, and I'll write that down right away. So x equals 10. So what we'll do for this graph here is we're going to scale that to be 10, and we'll scale that to be 20. So we have a vertical asymptote at 10, and at 10 and 1/10, which is very little, it's going to be -2. And then at 11, so remember this is 15, if you want to write this down. So this is 11, and we have -1. 20 will be 0. And then 110 way to the right side, it will be 1. So this graph increases very quickly, but then it also flattens out a lot. So it looks like this. So from the graph, we can see that the domain is x is greater than 10, and then the range is all real numbers, even though it's growing very, very slowly. There is no y-intercept. And then the x-intercept, which we can see there's only 1, this would be 20 and 0. If you didn't have the graph, you can also find the x-intercept by plugging in 0 for y and then solving for our x value. So move the 1 over. And then remember, this is a base of 10, so we can rewrite this in exponential form. So this would be 10 to the 1 equals x minus 10, so x is equal to 20. All right, so the second part here is I'm going to show you how to graph using a table of values as opposed to transforming, because I think that's also very valuable. So it's going to help to identify the asymptote first, and that will give you a starting point. So let's graph this we're going to graph this log by changing it to exponential form and then using a table of values, and then we're going to identify these characteristics. So first, let's rewrite this in exponential form. So this will be x plus 3, which is our answer, is equal to 5 to the power of y. So x is equal to 5 to the power of y minus 3. So remember that this equation, or this function here, is actually identical to this one. They're just in different forms. One's in log form, one's in exponential form. So in exponential form, I'm going to find y values and then solve for the x. So we know that let's just start with some negative ones. So we have negative 1. I plug it into here. I get 1/5 minus 3. So I get negative 2 4/5. And let's increase to 0. So now we have 1 minus 3. That gives us negative 2. Plug in 1. 5 minus 3 is 2. Plug in 2. We get 25 minus 3, which is 22. So start with your asymptote when you graph, so that guides you what not to cross. And here we have x is equal to negative 3 based on this part of the log function. So we're going to graph using a dotted line for the asymptote. And then we're going to plot these 4 points. And connect them. Now we can't graph the 22, but we know that it's way down over here. So we can see that the domain is x is greater than negative 3. Range is all real numbers. And the x-intercept, you can see from the graph, is negative 2. But let's say what you couldn't find it, you can go x equals 5 to the 0 minus 3. So then x is equal to negative 2 as well. So I've shown you how to graph using transformations, and I've also shown you how to graph using table values. And it's nice to be able to do both, so that if one method doesn't work very well for you, you can try the other one. To finish off, I'm going to show you how to find the equation given the graph. So here we have the graph of y equals log x with a base of 3, and I want you to write the equation that describes this new graph, this black one down here. So it says that it's only been translated, which is kind of nice. So all we need to do is to be able to pick a point that's moved from one graph to the other. So I can see that probably this point, and you can see that there's the way that it's curved here, it kind of matches this part over here. So we're going to see that this point is now moved over here. And from here, we can see that that point has moved 2 to the right, and 1, 2, 3, 4, 5 is moved 5 down. So therefore, if this was my original function, then we can say that this is going to be log with a base of 3. So the base doesn't change, it stays the same. Right 2 means that it's going to be x minus 2. And then 5 down means that we need to put the minus 5 on the outside of the brackets and after the log. So there you have different ways of looking at logarithmic graphs.